Okay, so finally, at long last, we're ready for chapter three. So, what's going on in chapter three? Well, we're going to see some of the most important applications of all that content we did in chapter two, where we first learned about derivatives. Okay, so this is a very important chapter because we're going to see how we can use calculus to find the solutions to a lot of very complicated problems in the real world, in particular, optimization problems, which involve finding the maximum or the minimum value of a function, which is something we do on a regular basis in applied math. So let's begin by introducing the concept of extrema. Now, I just want to mention some terminology here before we get any further. Um, First of all, we know that within any given interval, a function may take on a maximum value or a minimum value. Now, here's one of the quirky things about English. We have a lot of Latin words mixed into the English language. So the rules for pluralization can sometimes surprise us. And here's a perfect example of this. The plural of maximum is maxima. And of course, then the plural of minimum is minima. Whoops, minima. I didn't spell it correctly. Oh, it did it again. Minima. Okay, there we go. Now, the word extremum can refer to either a maximum or a minimum. And as you can probably guess, the plural then of extremum must be extrema. Okay, so I just want to get that straight right up front because this is what we're gonna be talking about for the rest of this chapter, basically. So the title of this chapter, or the section, I should say, is extrema on an interval. So this is what they're talking about. They mean within any given interval, there can be more than one maximum, there could be more than one minimum. And so we need to think in terms of extrema, which means it could be any combination of a one or more minima or one or more maxima. Okay. Now, of course, sometimes there aren't any extrema at all, but the word extrema refers to both. Okay. All right. So let's begin. Um, so a lot of effort is like it says here, devoted to determining the behavioral function, but specifically with respect to whether or not it has a maximum value or a minimum value, or is it increasing or is it decreasing? These are critically important questions that we have to ask ourselves in calculus. So now, of course, you have to visualize there's some function here. Let's say it looks something like this. And the interval of interest, let's say, is from here to here. So you can see it's a very complicated looking function, and there are regions within which it does appear to be increasing, and other regions where it appears to be decreasing. And then there are also points where it seems to reach a peak and then turn down afterwards. And there's also regions where, or like here, for example, it seems to bottom out and then it starts turning up again. And also at the end points, we might be reaching the highest value within the interval, or possibly at the left-hand point. So in other words, we're looking for these points where the function has some specific behavior. And so we're going to start out by defining what we mean by the word minimum. So here's our interval, and f of c is the minimum. Let's see. If I've drawn this right, My goal was for this to be the minimum. That would make this point C, and this is f of C. Okay. And so this is known as a minimum on the interval I when f of C is no more than f of x for all the points in that interval. Okay. There can be a tie, but we don't have, in other words, what we're saying here is that there's no other x in this interval where f of x is less than f of c. And that makes this a minimum. Now, of course, it's only true for that interval. There might be other parts of this function where this is not true, but this is the interval of interest. This might be, for example, let's say that this curve represents the cost of producing a product of some kind. And I'm interested in finding the point at which that cost is minimized. Well, that would be the answer right here. C, if I produce C units of this good, my costs will be as low as possible. Okay. Now, of course, we may have the opposite. Um, let's try something like this. Let's say this is my interval, and this is the point C, and this is f of C. I'm sure you can guess that this is going to be referred to as a maximum over the interval from I to B, A to B rather. And that's because f of C, as you'll see in the definitions here, is at least as great as f of x for all x in the interval I. Okay, now sometimes it's obvious just by looking at the graph, sometimes it isn't, but this is what we're aiming for. Okay, great. Now, we can then make a distinction between what are called relative extrema, which are sometimes called local. Let me just fix that. Now, this is only true if there's more than one. We can also have what's called a global or absolute extrema. Let's say, for example, you've got something like this going on. So this is A, this is B. Now here's a point where the curve drops and then it starts to rise again. But here's another one right here. So what's going to happen here is that both of these can be treated as minima. The difference between the two, let's think of this as C1 and f of C1, and this will be C2 and f of C2. So within this immediate area here, we can think of this one as what's called a local or relative minimum. because it's the smallest value, but only within that immediate, sometimes it's called neighborhood. F of C2 has the same properties, but it's smaller than F of C1. So because it's the smaller of the two, F of C2 is known as the global or absolute minimum. Okay, so in other words, there's two of them. They're very small within an immediate that immediate vicinity. Of the two, C2, F of C2 is smaller, and so the name changes to global or absolute minimum over this interval, of course. This is all with respect to the interval here. Okay, so now if sometimes you'll have a function where the extrema can occur at the endpoints, like uh, like in this case that I just drew. We have several candidates. Actually, no, this one doesn't count, so never mind. But um, we may as well just I'll tell you. No, let me draw a new graph for this one. Otherwise, it'll get very cluttered and very confusing. So we've got two relative or local maxima, and of course, the same thing can be said for C2. But of the two, FC2 is larger. And so therefore, F of C2 becomes the global or absolute maximum. And again, this is only with respect to this interval I, not for the entire function, only within this interval. Okay. And then, yes, like I started to say, the endpoints can also satisfy this role. Whoops. Now, because this is the largest value in the interval, we can call it the the global or absolute maximum. Whoops. But it might sometimes they also hear it called an endpoint maximum. Okay, so there's what an endpoint, yes. Okay, and the same thing can hold with minima. So in other words, just to make sure it's clear that this represents the endpoint, sometimes they use that in terminology, but much of the time we'll either refer to the points as either local or relative maxima or minima or global if it's just the one largest. There's only one global. There can be many locals, but there's only one global. And in some cases, there doesn't have to exist a maximum or a minimum. But the ones that don't have one are relatively strange cases. But you can see that an interval can have a fairly large number of maxima or minima, but there's only going to be one global. Okay. All right. Now, here you've got some interesting cases. Let's copy these into the notes. Now, here the interval is the closed interval on the left from -1 to 2. And here we go. Now, in each case, there's only one minimum and there's one maximum. So we can think of this as global and global. Okay. Well, they're actually technically both. Um, but the one on the right doesn't have a maximum because of this hole here. In other words, the interval itself is open. So 2 itself is not actually in the interval. So while it does have a maximum, it's not the endpoint. Okay. Because that is not part of the interval. So when we talk about intervals, we have to be very clear about whether it's open or closed. Or possibly, there might be one side is open and one is closed because you can see here we have these holes. But sometimes we run into cases where you might have, let's say, this endpoint is included, but not this one. So remember, the square bracket means that's part of the interval. The open or round bracket means that it's not. But you could also have this. Okay, so it's very important to pay attention to whether the interval is open or closed, or half open, as it's sometimes called. That'll affect our results. Okay. Um, Now here, oh, look at this one. We've got a hole in the middle. So this function is discontinuous. Now that's something else we have to watch out for. Up to this point, we've been assuming that all these functions we were looking at were continuous, at least over the interval of interest. What if that's not true? Oh no. Well, that means this can't be a minimum. The function is discontinuous because there's a hole in it. Okay. And in fact, you can see this is technically um, a piecewise function because they filled in the gap at 2, and then the rest of it is x squared plus 1. X is not equal to 0. So what they're saying here is that there's no maximum. Sorry, no minimum. Okay. Now, the extreme value theorem. Now, in this chapter, we're going to introduce two very important theorems. Now, theorems are helpful because they can state conditions that are either always true or only true under certain conditions. And that can help us a lot when we're looking for results. If we have a theorem that guarantees that a solution exists, for example, we're not wasting our time looking for a solution that doesn't exist. Now, in a very advanced class, they might actually ask you to prove some of these theorems, but that's not going to happen here. You probably have to wait till at least whatever comes after Calc 3 before you get to that point. But for now, we're just going to use the results. So the extreme value theorem says the following. If the function is continuous over a closed interval, AB, then that guarantees the existence of a minimum and a maximum over that interval. So, in other words, if you're looking for them, you're not wasting your time because you know they exist. All right. So, in other words, I mean, if you imagine like doing this with a graph, as long as there's no gaps in the curve, no matter how you draw it. And by the way, the reason why it's important for the interval to be closed is because the endpoints themselves might be the maximum or the minimum. That's why that's an important detail. It might be that there's no minimum or maximum in the interior, but at the endpoints we may have our maximum or minimum or one of the each. So no matter how careful or how strange this graph looks, as long as it's a function, it's got to have a maximum and a minimum in there somewhere. It doesn't tell us where they are, but we're guaranteed that they both exist. Okay. And it could be the endpoints themselves that represent the maximum or the minimum or both, one of each. All right. Now, um, how do we find them? All right. So let's see. We're going to start with this one. Let's see. No, I guess we're not going to do that one. All right, let's start with their first example. F of x. All right, so assuming that we have a closed continuous, a continuous function over a closed interval, in other words, the requirements for the extreme value theorem are satisfied, here's what's going to happen. We've got f of x is x cubed minus 3x squared. And here's roughly what it looks like. All right, well, that's not the best, but it'll do. And the closed interval is, oh, they didn't give us a closed interval. Now that could mean that it covers the entire real number line. That qualifies as well. So I think all they wanted you to see is that visually you can see where these points must be. So this is our maximum. I should say relative maximum. Now, again, the idea is that this is the highest the function will reach within that immediate area or neighborhood. Having said that, you can see there are points up here that are higher. So the global maximum will be over here somewhere. But this one qualifies as a relative maximum. And then over here, we have a relative minimum. And again, the way to think about it is that um, they're describing it as the top of a hill and the bottom of a valley. Okay, this is how you can visually see where to find these. But I would like to point out here two important things. And this is something they'll mention later on anyway, so I'm not telling you anything you're not supposed to know. But for each of these, the tangent line, so if you drew a tangent line to that point, here, for example, and here, the tangent line has a slope of zero, meaning that it's horizontal. The other thing to note here is that at these points, the slope of the curve um, changes from either positive to negative, and that would be the case for the relative maximum, as you can see, or the other way around, negative to positive, which is the case for the relative minimum. So in other words, there's multiple ways of determining if a point is a relative maximum or a relative minimum. Okay. Oh, what happened here? I seem to have lost a page. Yeah, I just want to clean it up a little bit. So you're not looking for, oh God, see, no, that's the problem here. Um, no, I think I can fix it. There we go. Phew. Yeah, I got to, with the handwriting, that's the problem. You got to be very careful with the spacing of it. All right, I think we're in good shape now. Anyway, so again, you can see just by looking at it, like the hills and the valleys, of course, but the tangent line to the curve at that point is flat or has a zero slope, and the sine of the curve itself, in other words, here the slope is going from positive to negative, negative to positive. Oh, you know what I should have done here? No, I wrote it correctly. The slope of the curve changes from positive to negative or negative to positive. Okay, good. So in other words, let's just fill these in. And then down here, the slope continues to be negative. Then it goes to zero. And then here it's positive. So when it changes like that direction, you know that you're looking at either a relative minimum or a relative maximum. Okay, so with all that being said, now if you notice too, it mentions the name relative extrema here. Okay, it's important to recognize that these are not necessarily global extrema. In fact, we can see that they're not. Like I mentioned here, clearly this is less than, let's say, this point. So these are relative extrema. Actually, so I probably should change this title here. Okay, good. Very good. By the way, sometimes you run into these very strange cases. Um, the relative extrema can take place in two different ways. As far as geometry goes, that is. So you notice how this one, they describe it as smooth and rounded. Okay, but if we had something like this, a sharp, sudden break, um, this, by the way, is the graph y equals absolute x. This also counts as a relative minimum, in spite of the fact that it goes sharply from one slope to the next. In other words, over here, if you notice, the slope is -1. The slope here is +1. Whereas over here, the slope is negative, but it's getting progressively less negative. Here it hits 0, and then it's becoming progressively more positive. So, in other words, in spite of the way it looks, this still counts as a relative minimum. Now, if there's an open interval which contains a maximum, of course, then we call it a relative maximum, and then we have the relative minimum. So they're making sure it's clear that we these are relative maximum. Now, there could still be a global maximum, but if f of c is the smallest within a given region or neighborhood, then it becomes a relative maximum or relative minimum. Ah, we've got some nice graphs here for us. All right, well, it should be pretty clear. And these are very, very straightforward cases. Relative maximum, relative minimum, as we already saw this case. And then we have a relative maximum and a relative minimum. Okay. Now, they're giving us another hint here as a way to identify these points. I would like to remind you that, let's say we have something like this. No, let me try something a little different. Okay, so it should be clear by looking at the graph that this is our relative minimum. It's also clear that the tangent line has a slope of 0. How do I identify this point? F prime of 0 is 0. In other words, if I take the derivative of this function at this point, it'll have a slope of 0. Okay? Because remember, The first derivative is just telling us the slope of the tangent line at that point. So I'm looking for the one specifically where the slope is zero. So here's what we'll do. We'll use the power rule to solve for 2x, set that equal to 0, and then we'll find our x. Now the y is easy because y equals x squared minus 2. So the point 0, -2 is our relative minimum. Okay, so in other words, now this is the first time they've mentioned it. They're reminding us here that if you did take the derivative of this function and set it equal to 0, you will find any point that you find will either be a relative maximum or a relative minimum. Okay, they all have the same property. Huh. Now, they do also want to mention here, this is something I'm not sure if this ever came up before, but this one, you notice how it says f prime of 0 does not exist. So the thing about the derivative is because of the way it's defined with limits, I think we even used this example when we introduced limits. It sounds familiar. I'm still getting used to drawing on this tablet, as you can see. It's fine for just straight ahead writing, but for drawing, I don't know. All right. Okay, here we go. So the limit as x goes to 0 from the left and right, well, they're both 0, but the thing is, the where we're getting into trouble is that there's a sharp break between the left and the right. That's what I'm trying to get at here. Okay. So in other words, the slope suddenly jumps from -1 to +1 at x equals 0. And that means that f prime of x at x equals 0 does not exist. In other words, for a derivative to exist, the curve has to change slope very slowly or very subtly, I guess, and not jump directly from one to the other. If it does, then the derivative does not exist or said to be not defined. So in spite of that, we still have a relative minimum. Okay. So in other words, what they're building up to is this idea that we can find the points where it has a relative minimum or maximum by identifying any points at which one of two things is true. Okay. So in other words, when it comes time, let's say they give you a function and say, here's a function, here's an interval, identify the relative maxima and minima. What you would do is you find all the points where the derivative is equal to zero, because that means the tangent line is flat, or there's a sharp break in the curve, which means that the derivative does not exist. Those are your relative maxima and minima. So let's see, what did they do with this next? By the way, I do want to mention here, though, that what they still have not discussed with us yet. Oh, this is what I was trying to remember before. The limit, not of x, absolute x itself, but absolute x over x changes suddenly from -1 to +1. And that's why the derivative is or does not exist at exactly x equals 0. Okay, that I was trying to remember how that works. And so here it is right here. Yeah, as I started to say, um, what this is nice as far as it goes, but this would be true. Here's a function, and here we have f. Let's say this is, let's call this C1. And here's C2. And let's say we're only looking at the interval. Hold on. From, let's say here's A and here's B. Well, yes, of course, you can see those are the extrema, relative extrema. But here's the thing. How can you tell which one is a maximum and which one is a minimum? That has to be addressed next. In other words, we still don't know how to separate them from each other. At the moment, all we know how to do is tell which ones are extrema. There's still one more condition that we need to determine which ones are relative maxima and which ones are relative minima. So we'll get to that very, very soon. But here it's enough to note that these are my 2 points at which I have, in one case, a relative maximum and the other relative minimum, because the tangent line is flat, meaning that the first derivative is 0 at that point. Okay. Let's see. So critical numbers. Now, here they're giving us a couple more examples. What they're telling us, and this is just definitional, is that we know, because of what we discussed earlier, that this must be a relative extrema, or a mum, because f prime of c does not exist, as is this one. So they're going to introduce a new concept. This is just a definition. The point at which this happens is called C, is called either a critical number. Some books call it a critical value of f. Okay, so when you see that terminology, critical number, critical value, it means it's a C, a constant C, such that either f prime of c does not exist or it is equal to 0, and therefore this point must be a relative extremum. Okay, so now, of course, the challenge will be to find them. So let f, this is the formal definition, f is defined at C. Of course, we have to assume that already exists. In other words, we're assuming that there's no gaps in here. Okay, we don't have a hole. Um, if f prime of C is 0, which means you have a flat tangent or not differentiable because there's a sharp break, then C is defined as a critical number or value of the function. And the reason why this is important is because the relative extrema can only occur if C is a critical number. Okay. So to find extrema means we're looking for the critical values or critical numbers. All right. So we're going to do this. We're going to see the procedure on a closed interval. All right, here we go. So to find the extrema of a continuous function on a closed interval AB, we start by finding the critical numbers. So in other words, we're looking for all the points where the slope of the tangent line is 0 or does not exist. Evaluate the function at those points. Do the same thing for the endpoints, just in case they are the extreme points. And then of all of the ones you find, the smallest one is the minimum, the largest is the maximum. All right, so let's do an example of this. A nice straightforward one. I like it. There's no cosines or anything in here. Um, so here's our function. By the way, why don't we take a look at Symbol Lab because, it'll give us a better sense of what we're looking for. And in fact, it'll actually tell us where the extreme points are. So, but we're going to find it the traditional way, but we'll know the answers in advance. Okay, here we go. Wow, that's a weird graph. So it looks like there's only one negative one. Now you notice how they've labeled it global minimum, and that's because there's no other Well, first of all, there's no other minima in the first place, but if there are, none of them are smaller than this one. So it's both a local and a global minimum, and that's all we have. These don't count. Okay, those are just where it crosses the axis. That's it. It's right there. The point one, negative one. All right, so let's confirm this. I'll just write that there so we don't forget. All right, here we go. Let me see if I can sketch this. Look at this thing. This is what we're looking for right here. Okay, so based on what we said earlier, the first thing we're going to do is take the derivative. Actually, no. Let's go through all their steps because they have to tell us what the interval is. -1 to +2. So let's say roughly from here to let's say here. Great. First find the critical numbers. All right, great. So we take the first derivative using the power rule. And set that equal to 0. Okay. All right. So divide out the 12s. Then we'll divide out both sides by x squared. X equals 1. Beautiful. And that's it. That's the only point where this is happening. There's only one point in this interval where the tangent line is horizontal. Okay, let me try that again. We know this is a relative extremum, but is it a minimum or a maximum? Now, we kind of cheated a little by looking at the graph on Symbol Lab, but what if we didn't have this in front of us? How would we figure it out? Um, so, oh, you know what? That's an interesting point. Zero counts too, doesn't it? Yeah, because execute, yeah, that's it. That's true. So technically, those are both critical numbers or critical values, but only one of them from the graph you can see is actually an extremum. All right, so uh-huh. So what they want us to do, oh, I see what happened. You know what? I just didn't draw it right. If you look at the actual curve, you can see that the slope is actually zero at that point. Yeah, if you did draw this correctly. Okay. Now here's the interesting thing. This is a critical number, and so is this. And yet you can see very clearly that 1 negative 1 is a minimum, but 0, 0 is not an extreme point. It's neither. So this is an example why we have to be careful with our definitions because what it's saying here is that a an extremum must occur at a critical number, but not every critical number. But let's put it this way: not every critical number results in an extreme point. Okay. In other words, in order for it to be a minimum or maximum, we must be at a critical number. But the fact that it's a critical number doesn't guarantee that it's a minimum or a maximum. Okay, so we have to keep an eye on that. All right, anyway, um, so what else would they like us to do? Now, if you go back to the steps, you'll see that we evaluate the two. What we still are supposed to do is check the endpoints. Okay, so what are the endpoints in this case? Let's see. Well, we know that the interval covers the area from -1 to 2. So what we need to know is f of -1, which is 7. And over here, we need to know f of 2. 2 to the fourth is 16. 2 cubed is 8. So this is the point 2 comma 32. So these are potential candidates for being extreme points as well. Oh, and this is, I just mentioned this. The critical numbers do not necessarily result in extrema. And so they're also pointing out here. Now, this is, you can tell just by looking at the graph. No matter what value we pick in this interval, this point, there's no point in this interval that is larger. In other words, the function does not ever go past 32. Oh, actually, no, what am I doing here? Um, oh, I see. Sorry. This is 48. Sorry about that. No wonder it's wrong. It's 16, sorry. So in other words, this 232 should have actually been 216. That's better. So, but that one is actually a global maximum. This is a relative. Well, this is actually a global minimum too, because it never gets below that point. Now, later on, they're going to show us how to distinguish again between global and local, but here they're just simply referring to them as the minimum and the maximum. But you can see from the graph that they're both global maximum. One is a global minimum and one is a global maximum. And as I mentioned before, not every critical number is equal. It doesn't necessarily result in an extreme point. And that's what happened here. That 0, 0 is, yes, technically it's a critical number, but you can see it's neither a maximum nor a minimum. All right. So now we've got a couple of cases. Now here they just very simply want the critical numbers. Um, so this is a very straightforward example. Because all you're doing is taking the first derivative and setting it equal to 0. So we use our old friend, the power rule. Okay, now here's what we can do. Um, so we don't want to just divide out by x. In fact, I'll tell you what I probably should have done instead of this? Yeah, this is where we want to go. This way it's easier to see if there's anything that can be factored out. Yeah, this is much better. So this equation leads us with the following results. So there's three of them. All right, and that's all they wanted to know. That would be B. All right. And then what else do they have for us? Find the absolute extrema over the closed interval 0, 4. Okay. G of x equals x cubed minus 12x. So we can just drop out that 3. So we're going to wind up with plus and minus 2. And I think what they want us to do is evaluate it at these two critical numbers and the two endpoints. All right. X cubed minus 12x. So we'll do all of them right here. Well, I guess we could start with the endpoints. And then for the two critical numbers, interesting. And then G of 2. So we have the points 0, 0, 4, 16, negative 2, 16, and positive 2, negative 16. So I think what we should do is take a look at the graph in Symbolab. What is it again? X cubed minus 12x. Oh my God, look at this thing. And the interval of interest will include all of this part. So we've got a maximum and a minimum. And uh, let's see. Let me just double check something. It's 4 cubed minus 12 times 4. No, that's right. That's 16. And then the minus 2. See, it's hard to tell from this graph, but it looks like the 416. Well, we got these two right. I don't know why they're leaving out this negative 216. Is that correct? Minus 8 plus 24, that's 16. So if you look at the graph, they're defining 2 -16 as the absolute minimum, which makes sense. And of course, this is a maximum, but because they've included 4 in the interval, they did say that that's a closed interval. That's very strange. Well, it's an endpoint maximum, but still, I guess they only wanted us to look at these two. Um, I don't know. It's a little strange, but these definitely are minimum and maximum points. But they only mentioned the two of them, so I'm not sure why that. Maybe it's just because it's an absolute, it's multiple choice, but um, no, it does say only locate the absolute extrema. All right. Well, I mean, I guess the logic is that there's only going to be one, and they're going to choose the endpoint to be the global maximum, even though there's a tie. They're going to call that one the global maximum. So, or absolute maximum. It means the same thing. So, anyway, so what's coming up next? This is 3.1 we just finished. 3.2. So a couple more theorems. Now, remember we mentioned before there were some helpful theorems. These two, we'll see they can be very useful. They essentially state the conditions under which, well, we'll see when we get to it, okay? But they seem very abstract, but you'll see that they can be very useful. And then we'll get on to some more applications. So I guess we'll stop it right here. But you can see this is a very, very intense chapter, but it's awfully, awfully important. So we'll carry on from here the next time we meet with these two theorems, Raleigh's theorem and the mean value theorem. So I'll see you then.